Here's how OpenAI solved the problem that made voice AI interrupt you. For years, talking to an AI meant getting cut off or sitting through dead air. The cause was one small model, whose only job was to guess when you had stopped talking. Guess too soon, and it cuts you off. Guess too late, and the answer feels sluggish. The large model could not start until that tiny one made up its mind. The smallest component was setting the ceiling for all of it. In 6 months, OpenAI rebuilt the stack to delete it. GPT-Live is OpenAI's third-generation voice system. Its voice model is full-duplex, which means it can listen and speak at the same time. That single property is what removes the need for a turn detector. Audio streams into the model, and speech streams back out, continuously, on a dedicated fast path. And when the conversation needs real reasoning or a tool, GPT-Live can consult a frontier model like GPT 5.5 without interrupting the flow. 6 months of work went into this. They reworked model inference, context management, and media transport. So here's the shape of the system. Everything in blue is the live path. Everything gray hangs off it and runs asynchronously. And that gives us the one rule that explains almost every decision in this video. Nothing on the live path is ever allowed to block. Everything off it is allowed to be slow. To see why this is hard, start with the first generation. Cascaded systems chain 3 models together. Speech-to-text turned your audio into a transcript. A language model read the transcript and wrote a reply. Text-to-speech read that reply out loud. 3 stages in series, each one waiting for the one before it. The latencies do not overlap. They add. Put rough numbers on it. If transcription takes 300 milliseconds, the language model takes 600, and speech synthesis takes another 300, you have spent 1.5 seconds before the user hears a single syllable. And that is with nothing going wrong. Transcription also throws away everything about how you said it. Your pace, your hesitation, your tone, all flattened into words on a line. The model reads you, but it never hears you. And the deeper problem is inherited. This architecture is a text chat bot, with audio bolted onto both ends. Nothing in it is built for a stream because nothing in a text conversation is a stream. Second-generation systems fix the cascade. A speech-to-speech model takes audio in and produces audio out. One model, no transcript in the middle. Tone survives. Latency drops. This was real progress. But look at what stayed. The turn detector is still there, because inference still could not start until something decided your turn was over. And that decision has no good setting. Make the detector eager, and it fires on the pause you take to think, on the breath in the middle of a list, on the rhythm of someone speaking a second language. You get cut off. Make it patient, and every single exchange picks up dead air at the seam. The conversation feels like it is buffering. There is no threshold that is right for both, because the same silence means finished and means thinking. And here is the part that really hurts. The expensive model, the one that actually knows things, sits completely idle while the cheap one deliberates. The smallest model in the system decides how responsive the largest one is allowed to be. So the model was doing more of the work. But the interaction was still taking turns. The fix is to stop asking when the user is done and put the model in control of the conversation instead. A full-duplex model is listening while it speaks. It hears you interrupt. It hears you go quiet. It hears the sound of you thinking. So it does not need anyone to tell it when to talk any more than you do. But remove the detector and something more important changes with it. The system's job description changes. It is no longer answer this request. It is sustain an uninterrupted media loop. That is a completely different engineering problem, and it reorganizes everything around it. Reasoning, tools, saving the conversation, showing a transcript. None of that is part of the loop anymore. All of it moves off to the side. Which is the rule again, and it is worth saying properly. Anything that can wait must not be on the live path. So here's the first architectural decision, and it shapes everything after it. Audio moves between the client and the voice model on a dedicated fast path. Delegation, tool calls, policy, business logic, All of that sits behind an asynchronous boundary. And the consequence is the whole point. A tool call that takes 900 milliseconds delays its own result. It cannot stall the audio. A degraded backend service degrades that service, and the conversation keeps going. If those two kinds of work shared a code path, the slowest thing in the system would set the pace for the fastest. Networking has known this for decades. It is a data plane and a control plane, kept apart precisely because they have different latency contracts. The data plane forwards packets and is never allowed to think hard. The control plane thinks hard and is never in the packet's way. Same idea, new domain. There is a second benefit that is easy to miss, and over time it might matter more. That boundary is also where you customize. Applications can change their tools, their policies, their whole backend without touching the media front end that keeps audio moving. The live path stays small, predictable, and boring, which is exactly what you want from the part that cannot fail. And that is the general lesson here. Latency isolation is not something you tune. You do not get it by profiling and shaving milliseconds. You get it by drawing a boundary and then never crossing it synchronously. Now, keeping that loop fed is harder than it sounds. A request-response service can absorb jitter. If a reply takes an extra 50 milliseconds, a spinner spins a little longer and nobody dies. A live media system has no such slack. Every audio frame has a scheduled moment to exist, and if it is late, you hear it. A click, a gap, a robotic smear across a word, there's no retry that is fast enough to matter. Two things came out of this. The first is a rewrite. The media front end and the inference logic move from Python asyncio to Go, and the result is the single most quotable number in the whole write-up. The new system's P95 matches the old system's P50. Read that again. The bad case of the new system is the typical case of the old one, which tells you exactly what to optimize for in real-time work. Not the average. The average is a story about the frames that were fine. The tail is where the audible failures live, so the tail is the product. The second thing is transport. WebRTC, because it is built to survive packet loss, clock drift, and a client walking from Wi-Fi onto cellular. When a packet is late, its jitter buffer can stretch the audio slightly to cover the gap, then speed playback back up to catch up to real time. And underneath all of it, one discipline. Minimize buffering everywhere, because a buffer buys smoothness with latency, and here you have almost none to spend. Here is a problem that stateless serving simply does not have. A voice session stays open for a long time. Its context grows the entire time it is open. And the model instances underneath it are scaling up and down with demand all day long. You cannot drain a live conversation the way you drain an HTTP request. There is no convenient moment when nothing is in flight, because the whole point is that something is always in flight. Their answer is a seamless handoff between model instances, and it is worth walking through slowly. Step 1. Warm a replacement instance alongside the one that is currently talking. Step 2. Pre-fill it with the current session context, so it knows everything the live one knows. Step 3. Run inference against both of them, in parallel, for a while. Step 4. Cut over once the new instance is genuinely ready. The media never stops. Now, if you have deployed software before, you have seen this shape. It is blue-green deployment. What is unusual is the scope. Not blue-green for a service, blue-green for a single conversation. And notice the price, because it is a real one. During that overlap, you are paying for two instances doing the same work. That is the trade. You spend inference to buy continuity, deliberately. Now watch that same mechanism earn its keep a second time. Let a conversation run long enough and its context outgrows the model's limit. The usual answer is compaction. Summarize the old turns, shrink the context, carry on. But compaction costs twice. It takes time, and because it rewrites past context, it invalidates the key value cache, the stored attention keys, and values for every token already processed. An invalid cache means a fresh prefill. And a fresh prefill in the middle of a sentence is exactly the audible delay this whole system exists to avoid. So do not compact in place. Compact off the live path. Build the replacement instance with the new, smaller context. and then swap, using the handoff we just built. One mechanism, two completely different problems: scaling and compaction. That reuse is not a coincidence. It is what a good abstraction looks like. And it means the system can hold a genuinely long call, compacting whenever it needs to, without the conversation ever noticing. Which brings us to the most interesting piece. GPT-Live decouples talking from thinking. The voice model talks. A frontier model like GPT 5.5 searches, reasons, calls tools, and its results get folded back into a conversation that is still happening. Two models, one apparent system, making that feel like one system meant solving two problems: speed and representation. Speed first. The whole delegation loop is inside the responsiveness budget. Not just inference. Routing, prompt processing, inference, and tool calls, all of it. They're optimizations in order of leverage. First, pre-warm. When the voice session starts, the application server creates the frontier model's inference session and pre-fills it with the initial context. So by the time the first delegation is actually requested, that prompt has already been processed. You pay the setup cost at the one moment when nobody's waiting. Second, keep it and pin it. That inference session stays alive for the whole conversation, with stable session affinity for successive requests, plus prompt caching. So later requests hit a warm cache instead of re-pre-filling, and a worker failure is still recoverable. Third, tune the things that decide when a useful result arrives. Reasoning effort, output limits, tool schemas, the number of round trips between the model and its tools. And there's an honest constraint here that I like. The voice model can hold the floor for a moment. It can acknowledge you or ask a clarifying question, while the frontier model works. But it cannot hide an arbitrarily slow answer. Filler only stretches so far. So the target is not time to final answer. It is time to first useful result. And that distinction is what makes a two-model architecture feel like one. Now the representation problem, and this one is subtle. The voice path is a continuous stream, but the systems around it are not. ChatGPT's conversation view wants messages. Analytics wants messages. Parts of the safety infrastructure want messages. So the application server has to reconstruct discrete turns out of overlapping speech. It works like this. As audio arrives, partial transcripts and timing signals are used to infer who currently has the floor, building up a queue of messages. The newest message is provisional. Its text can change, its timing can change, even its speaker attribution can change, as more speech arrives. Only once a speaker has held the floor long enough for the attribution to be reliable does the server finalize it. Overlap makes this genuinely hard. If the assistant says, while you are still talking, that should probably not become its own message. But if it interjects something substantive, it probably should. And a displayed assistant response should stay coherent even when you talk over the middle of it. Underneath all of that sits one general law. Every segmentation policy trades freshness for certainty. Commit too early, and you get fragmented history and unstable ordering. Wait too long, and transcripts arrive late, along with every feature that depends on them. Their resolution is to stop choosing. Keep two views: a speculative view of the current state, and an authoritative record of what was actually said. The interface can handle updates, so it reads the speculative one. Analytics cannot, so it waits for the final one. We have talked about the conversation. Now the moment before it, responsiveness starts when the user presses the button, because the media path has to exist, and audio has to be flowing before anything can happen at all. And every bit of that is on the critical path. Plain webrtc is surprisingly expensive to start. It predates the obsession with round trips that produce protocols like Quick, so its sub-protocols each solve problems independently and end up repeating each other's work. Every one of them brought its own anti-denial of service mechanism, even where the full stack did not need it. So they built Warp, the webrtc abridged round-trip protocol, and it takes media and data startup from 6 network round trips down to 1. It does that with backward-compatible changes. Piggyback the DTLS handshake over ICE. Use the faster DTLS 1.3 handshake. pre-negotiate the SCTP handshake, and pre-negotiate data channels, instead of using a separate protocol to set them up. That left one thing on the critical path: the signaling exchange that shares connection parameters. Instant Connect pre-negotiates those ahead of time, without reserving server capacity, and the server materializes the session when the first media packet arrives. If the parameters have gone stale, ordinary signaling is already running underneath, so the fallback costs nothing. Put it all together, and a client can start a session with a single UDP packet. And they published it as open specifications, working through the IETF, with support already landed in webrtc and Peon. One more piece, and for my money, it is the most valuable part of the whole write-up. A system can look fast on paper and stall completely under real traffic. So before GPT-Live spoke to a single user, they ran a silent test. A small, gradually increasing share of real production voice sessions was routed to both the old system and the new one. Advanced voice mode kept serving users normally. The new path ran inference in read-only mode, in the shadows. Real clients, real networks, real session lengths, real geography. And nobody heard anything different. 4 things came out of it. 1. Capacity is not GPU throughput. Voice sessions stay open in stream frames constantly, so the CPU side stream handlers, the queues, the network paths, all of them have to scale alongside inference. Under real load, a supporting component saturated well before their load tests predicted. Requests piled up, and latency compounded. So they changed the question. Not how many requests can a GPU handle, but how many concurrent sessions can the system sustain while keeping every frame on schedule. 2. Geography is first order. Routing a session to distant capacity adds delay in several places, so model rollouts started being validated together with regional capacity and traffic steering, with latency broken down by where the user actually is. 3. Some bugs are only reachable through time. Long sessions surfaced, memory and persistence pressure. Reconnects exercised compaction and state restoration. Ordinary client disconnects revealed races in the shutdown handshake. A short load test cannot find any of these because they depend on accumulated state. And 4. The real gap was observability. Metrics that conflated different sources of latency, dashboards whose averages hid individual unhealthy engines, configuration drift between what was tested and what was deployed. The fixes were granular telemetry, validation against known good configurations, staged ramps, and the ability to isolate or disable any single path quickly. By the end, the silent test was not a capacity test, it was a launch rehearsal. So, what transfers? 6 things. Separate the fast path from everything else, and make the boundary asynchronous. In real-time work, budget the tail, not the average, because P95 is what your users actually experience. Make migration a primitive. Warm, pre-fill, run both, cut over, then reuse it for scaling, for compaction, for upgrades. Pre-warm at the one moment when nobody is waiting. When the systems around you need a different shape than your core loop, do not pick one. Keep 2 views, speculative and authoritative, and test in production, in the shadows, before you test on users. OpenAI summed up their own design principle in 4 words. The voice must flow. I would put it slightly differently because it generalizes well past voice. Anything that can wait must not be on the live path. Follow for more.